Well, I know that delta G is equal to delta H under non-standard conditions, but we've already deduced the fact that delta H is independent of both pressure and temperature. And that means that I can write delta H under standard conditions in my expression for delta G under non-standard conditions. Then I have minus T times the change in entropy. But we've just worked very hard to calculate what delta S is under non-standard conditions. So I can borrow from this expression and insert that in for delta S, and that gives me delta H under standard conditions minus T delta S under standard conditions. And I immediately see a huge step, because that quantity is identically equal to delta G under standard conditions. Well, that's very convenient. But now I have another term. I have minus RT times the logarithm of the pressure of N2 times the pressure of H2. I have to raise it to the power of 3 for the stoichiometric coefficient. And then I have the pressure of NH3, ammonia, and I have to square that. All right, so now I have my expression for delta G. That's equal to delta G under standard conditions. And then if I flip the denominator and numerator in the logarithm, I can write this as plus RT times the natural log of the pressure of NH3 squared divided by the pressure of N2 times the pressure of H2 cubed. But there's one extremely important point, and that is that we can rewrite this as delta G under standard conditions plus RT times the natural log, and then we look at the functional form. We've got pressure of ammonia squared, pressure of nitrogen, pressure of hydrogen raised to the stoichiometric coefficient. That's identically equal to our reaction quotient Q. So that is the expression for which we can calculate delta G under any conditions, standard conditions, non-standard conditions, and this is one of the most important expressions in all of chemical thermodynamics. There's one more extremely important conclusion that emerges out of all of this hard work that we've done, and that is that we know that under conditions for which Q is equal to the equilibrium constant, and the equilibrium constant, we remind ourselves, is a function of temperature, it means that if I substitute Q into our hard-won equation for delta G under non-standard conditions, I know also that the value of delta G, because that represents the equilibrium case, delta G must be equal to 0. So if I substitute these directly, it means that delta G is 0. Delta G under standard conditions remains as it is, but log Q becomes log of the equilibrium constant, which is the function of temperature. But that means that I have a relationship now between the change in Gibbs free energy under standard conditions and my equilibrium constant. That's an amazing relationship. That says that I take an equilibrium constant that I measure by looking at ratios of pressure or concentration, and that has a direct relationship to the change in Gibbs free energy under standard conditions. So if I were to give you the equilibrium constant, you could instantly give me delta G under standard conditions. If I gave you delta G under standard conditions, you could instantly calculate the equilibrium constant. That's a remarkable fact. And we can represent K equilibrium then as simply e to the minus delta G over RT, or exponent of delta G over RT, and we have a relationship that will allow us to interconvert delta G under standard conditions with the equilibrium constant. So to summarize, there's a direct quantitative connection between free energy and the equilibrium constant. We know what it is. The position of the equilibrium in a reaction is determined by the sign and magnitude of delta G. We've already determined this for N2O4 and NO2. That is, with delta G being positive, it means that we have to go uphill in free energy, going from pure reactants to pure products. Now that doesn't mean the reaction won't take place. It means that the reaction proceeds initially down the surface of delta G, but now we can calculate delta G at every single position. And if we were to start with pure products, we now have a quantitative relationship. We can calculate delta G at every single point because we don't have to do the calculation under standard conditions. We can do it anywhere. That is, we can calculate delta G under non-standard conditions. All right, so let's summarize then. Let's recognize that the direction of the reaction proceeds depending on the composition relative to the minimum point in free energy, that is, relative to the point of equilibrium. We can write the change in Gibbs free energy, that is, the slope of that surface, quantitatively as the change in Gibbs free energy under standard conditions plus RT times log of Q. And remember, we always write Q as the concentration or pressures of the products divided by the reactants. And so this brings us back to our profoundly important relationship that we use in almost all aspects of thermodynamics, and it turns out we'll use it in acid-base reactions, we'll use it in electrochemistry. It is the foundation upon which we do all calculations under non-standard conditions.